right, chapter 8. Chapter 8 actually is one of those chapters that typically is pretty easy for students. We're going to get into statistics a little bit, but it's the very basic form of statistics. If you take an actual statistics class, you'll do a lot more than what we're going to do. We're going to keep it fairly basic here. So usually chapter 8 is usually is the best test of the semester when I teach it in a regular semester. So this should be, I'm hoping for good grades here on chapter 8. So it's on probabilities a little bit, so we will be using some of the stuff from chapter 7, but what we won't be doing is there won't be any vens, there won't be any conditional probabilities. They'll all be basic probabilities, and we'll be doing them in more probability distribution cases. And then a lot of the stuff we'll be able to do on the calculator or in, we'll have nice formulas and things with, when we get to stuff we'll do in the future. So chapter 8, not too bad. Most students succeed very well in chapter 8. Alright, so first of all, just like with chapter 7 and chapter 6, we start off with some new sort of definite math and language. We use our own words and our own terminology. Same thing with statistics. We use our own words, our own terminology, our own symbols. And so the first thing, when we've done a little bit with random variables when we did probability, right? We wanted everything to be equally likely when we were doing probability, and so it was always random. I randomly drew a card out of a deck. I randomly selected a handful of marbles. I randomly picked somebody from a survey. All right, it was all random. Same thing with 8. When we do statistics, things need to be done randomly, so there's no bias in the statistics. So random variables and probability distributions, which again, we've already talked about probability distributions in chapter 7. Remember, I hinted in chapter 7, we did it really early in 7.2. I hinted that we're going to do them here, but we'll deal more with probability distributions in chapter 8. And we will. We're going to do a lot with distributions here in chapter 8. Right, so first, the first sort of new terminology, kind of, is what we're going to call the random variable. And we're going to assign it x because that's what we do in mathematics. We tend to assign unknowns or things we're looking at as x's, right? And so the random variable x is a rule that assigns a number, alright, so it has to be a number, unlike when we did before where I could look at heads and tails and write out heads, you know, H for heads, T for tails. In statistics, I can't do that. What I have to do is I'm going to have to assign a number to what represents number of heads, a number that represents a number of tails. So again, my statistics is based on numerical values, so I have to have numbers. So my first example is going to be that tossing a coin. Alright, so x is going to be the number of heads in 3 tosses. So x is going to be, I can get 0 heads out, 1, 2, or all 3 could come out heads. And so that's what we mean. Instead of writing H for heads and then 2 T's for tails, or all 3 H's, we're going to assign it a number. All 3 means 3 H's. 0 means all tails, right? It is hidden in there. That means 1 head and 2 tails, right? 2 means 2 heads and 1 tail, and then 3 means all 3 heads in there. And so this is what we do in statistics. We can look at surveys. Survey would just be the number of the people in the survey. Right, or the number of people who answered a survey a specific way. Alright, it could still do with dice, but we would either be just looking at the number on the dice, actually it works out that way too, or the sum of the numbers on the dice, right, the sum of the numbers on a dice, 2 dice. 2 dice. Right, again, the key thing is we look at numbers, right? And there would be listings of numbers. Number of people who answered a specific way in a survey. Right? A number of people said yes. A number of people said no. A number of people said maybe. Right? Those would be numbers. Sum of numbers on a dice, right? I can get, if I roll 2 dice, I can get a sum of 2, a sum of 3, a sum of 4, a sum of 5. Those are all numbers. Actually, we can look at the dice example because they're already numbers. Right? If we look at just the dice, I can roll the numbers 1 through 6. But when we're looking at statistics here in chapter 8, everything has to be represented by a number. Right? Because we're going to run statistics on the numbers. There are 2 types of random variables. The first one, which is actually the one we've dealt with in chapter 6 and chapter 7, and we're going to deal more with here in chapter 8, is the one we use the most. It's called the discrete variable. And if you've ever taken discrete math, All right, you know what the discrete variable is. Discrete means it can only take on specific, isolated numerical values. Most of the time, it's your whole number values or your integer values. All right, but it doesn't have to be. Things could be separated by a half, right? If you were given at a quiz and you could score it from 0 to 10, but you get half points, you could get 0, 1, 1.5, 2, 2.5, 3, but that's it. You couldn't get anything else. You couldn't get 2.25, 2 and 3/5 or something like that. You get, they're separated. You can't have every value in the real numbers, right? You have to have specific numbers. For us, most of the time, it's whole number values because we're dealing with people and things. All right, so an example would be the number of people in a room. Right? I can't have a fraction of a person, right? I can't have 6.3 people in a room. I can have 6 people in a room or 7 people in a room. Score on a test. Like a standardized test, so something like an SAT. Alright, usually those are whole number values. The heads example up there, number of heads. In so many tosses. Right, whole number values. And like I said, you could get fractions, like suppose you get, the number on a test, but the test could give you maybe a half point, right? So it would still be whole number values plus the halves, but that's it. So it's not all possible values, it's just whole numbers or half values, or whole numbers with half values, like 1, 1.5, 2, 2.5, but they're still separated. It's separated by a half. All right, and it also means finite. Right, that's the other part of this. Finite. It means we could actually list them. Right, they're countable. They're not infinite. There's a specific set of numbers I can look at, and I could list them if I wanted to. All right, so again, they're finite. They're not infinite. This is the one we deal with the most. This is the one, like I said, in Chapter 6, all of ours were discrete finite random variables. In Chapter 7, discrete finite random variables. In Chapter 8, for the most part, they're going to be discrete finite random variables. Until we get to the end of Chapter 8, we're going to look at a specific case of a continuous random variable. That's the next one. But we're going to only look at one type. If you go into an actual statistics class, they'll look at many different types of continuous. We're going to look at the most common type, and really the easiest type. And we'll get there. This is what the last section of Chapter 8. So we won't get there till Chapter 8, but it is introduced here in Section 8.1. So continuous random variable means I can take out any value in the real numbers, right? Meaning all fractions, all decimals, rational or irrational, between any two numbers, right? So again, it's infinite. Right? This means I can have, because there's infinitely many fractions. If I go between 0 and 10, and I get to include all fractions, decimals, rational and irrational numbers, meaning square root of 2 is between 0 and 10, it's included, right? All numbers are included between 0 and 10. There are actually infinitely many numbers, right? Pi is also there. There are infinitely many numbers between 0 and 10. And so it's continuous because I get to pick anything from 0 to 10. It's continuous. If I were to draw it out, it's a smooth curve. When you draw out discrete variables, they're dots that are separate, right? They're not smooth. They're not connected, right? They're separate. Continuous, they're infinite and uncountable because it could take on any real number value on a given interval. Interval would be what you're looking at, right? And I'm looking at people. All right, so I'd have a certain number. I could go 0 to maybe 100 people, right? That's how many people would be in my survey. Or flipping a coin 3 times. It'd be 0 to, again, those would be examples of the whole number cases. But that would be the interval. Interval would represent, what am I looking at? What's my range? All right, so examples would be basically anything that's measured, right? When you measure something, depending on how good your measurement tool is, you can get out any decimal or fraction. And so weights, let's do weights of kittens, right? How much do they weigh? If you go into the ounces and you go to the, half of ounce, fraction of, 0.3, 1/3, 2/3, 1/10, 1,000th. Right, you can have as, depending how good your measuring tool is, you can have as many different weights as you want, right? There could be infinitely many weights if you weigh all the different kittens, right? Anything that basically is measured typically is in this case. Another example would be, suppose we put things in terms of percents, right? If I wanted the percent of students who are marketing majors. Now, if I just listed the marketing majors, that would be discrete. But since it's percent, right, I could have a 0.5%. Right, there's 62.5% of the students are marketing majors, or 62.1, or 80.5, or 80.25, or 80.55, or, you know, all the decimals can be included in your percents, right? Anything between 0 and 100%. Now that would be my continuous between 0 and 100%. I could have any percent, whole number, fraction, decimal between 0 and I got 0.5% if I wanted to, 1/3 of a percent, 1/10 of a percent, 1/20th of a percent, 1,000th of a percent if I wanted to get down to the, again, smaller I go. So there are, again, infinitely many numbers in that case. Right? Heights of people. All right, there tend to be, again, everybody's just a little bit different, and you could go down to small fractions if you wanted to. And you could go to the centimeter, the millimeter, you know, whatever. You can keep going smaller and smaller, micro values if you want to. All right, so again, this is when all fractions are in. You can look at all fractions, so all real number values over a continuous interval. And like I said, we'll only do one special case of this, so we'll do most of ours will be discrete. When we get to the end of chapter 8 is when we do a continuous random variable, and it's looking at a very special type of continuous random variable. If you actually take an actual statistics class, they'll go over more types. We're not. We're going to do the easiest case. But it is also the most common case. Alright, we're going to get to probability distributions. Alright, probability distributions for a random variable x, where x is discrete and finite. Alright, so probability, again, we're going to put it in terms of the random variable x, so we're going to say probability of x equals some number, right, because we're now representing anything by numbers. So instead of saying probability to get heads, I'm going to probability I get x equals 1, meaning I get 1 head. Or probability x equals 2, I get 2 heads. Probability x equals 0, I get 0 heads. Alright, so s has a specific numerical value that it represents something in number terms. And we're just going to practice that in a couple of cases, just to kind of get you ready, and then in the next video, we'll do distributions with random variable x. Alright, suppose I have 2 dice. I have a red dice that's 4-sided, so it's like a pyramid, 1, 2, 3, 4 on its faces. I have a green dice that's our 6 regular sized dice, which has the numbers 1 through 6. The 2 dice are rolled. The random variable x is the lowest number showing. Alright, so x would represent the lowest number in the pairs when I roll it. If I rolled a 1 and a 5, 1 would be what I'm looking at, because 1 is smaller than 5. If I rolled a 5 and a 6, though, 5 would be the smallest number, right, because out of 5 and 6, 5 is smaller. Alright, so again, if I rolled a 2 and a 2, 2's it, because they're both 2. So all the possible values for the discrete random variable x. And so if I were to do a probability distribution, what are my possible values? Well, 1 could pop up the smallest, right? So if I roll 1 with any number, doesn't matter, so again, I'm kind of looking here. If I roll a 1 with any of those, 1 comes out the smallest. If I roll a 2 on my red dice, well, 2 is smaller than 3, 4, 5, and 6, so a 2 can be the smallest. If I roll a 3, it can be smaller than 4, 5, and 6. If I roll a 4, it can be smaller than 5 and 6. But then I'm done, because this dice only rolls the numbers 1, 2, 3, and 4. So 1, 2, 3, and 4 will always be the smallest, because if I pair them with 5 and 6 are always bigger than 1, 2, 3, and 4. And so that's it. My discrete finite random variable is only possible for 1, 2, 3, and 4 to be the lowest numbers. Alright, the other example. Alright, suppose, so we're still going to have dice, we're still going to have flipping coins, we're still going to be picking committees of people. Alright, we're going to do an example in a little bit where we're drawing marbles out of a bag, so we'll still have all of those. But we're going to do them in the easier cases, meaning they're not going to be any continuous or conditionals. No conditionals. Right, suppose I have 3 women, 6 men that are eligible to serve on a committee. Alright, so the committee of 5, so committee combinations have already actually solved this. Alright, a committee of 5, and that's important that I know that. Alright, so I want to pick 5 total, right? I have 3 women and 6 men. Alright, so I kind of keep that in mind. List all the possible values where X represents the number of men in my committee. Right, I've got to count something, and we picked men to count. Alright, so X. Could I have a committee with all 5 members being men? Men, yeah, I've got enough for that because there are 6 men. Well, if I pick, the next would be, can I have a group with 4 men? Well, if I pick 4 men, I still have a woman to complete out my group, so that works. If I pick 3 men, I'm good because I still have 2 women to finish out my group of 5. If I have 2 men, I've got 3 women, but then I stop there because if I tried to get a group, if you tried to pick only 1 man, well, I have 1 man, and then I'd have to use my 3 women. Well, that's only 4 people. Right? And so my committee wouldn't be complete. Right, I want 5. I don't want 4. I want 5. And so I can't pick only 1 man. I have to pick more than 1. Right? I have to have 2, 3, 4, 5. I can't go less than 2. And so those are the only possibilities for my random variable X. Now, just so, again, this isn't in, when I fill out my notes, this isn't actually in there. If we done it the other way around and I let X be the number of women, so this is just an extra. Well, X could be, well, I could pick 3 women because I've got enough men. I could pick 2 women, right, because I have enough men. I could pick 1, and I could pick 0 in that case because if I have no women, I've got the 5 men, and these kind of pair. The 0 here for the women goes with the 5 men. The 1 woman goes with the 4 men. The 2 women go with the 3 men, and the 3 women go with the 2. And so they sort of pair up. And there's a way to double check your answer if you want to. All right, now the answer to this particular question, if it was a test or quiz question, would be 5, 4, 3, 2. All right, but that's just an FYI, kind of something that you can use to check. Alright, so we're going to stop there. The next one we're going to look at, next video we're going to look at is probability distributions and how they're represented graphically. Alright, so that's the next video.